because we'll continue discussing from here, okay, and looking at the segmentation module. We are recapturing it, okay. So what is this? This is each code block should be of size k dash, okay, which is b dash by c. B dash is the payload which needs to be transmitted, which includes what? B dash includes actual payload plus transport block CRC plus code block CRC, right? This is what you intend to transmit, okay. Now what we are saying here is it is not done like this, and the primary culprit is the LDPC encoder, okay, because it cannot encode 7072, okay. And in order to handle this, we know now attached to this each code block is basically the filler bit, okay. And how many filler bits we need to attach, that's what we are going to see now again, and I am taking you to this next lecture, okay. So that's what we are going to recap now, okay, right. So now we have to just like jog back into our memory, okay, and then what happens here is basically this, as LDPC needs to encode this. And how does LDPC encoder works? Okay, and works by generating something called this parity check matrix, okay, right. And then this parity check matrix cannot be generated for any arbitrary input length, input code block, okay. In order to generate this parity check matrix, what is defined is basically the base graph matrix, okay, and that needs to be blown up to the size of blown up to the required size, okay, and that blowing up process is called lifting, okay, lifting the base graph matrix, okay. And how much do you lift? That's what is decided by this table, and it contains these lifting size which the standard uses, okay. And now, so what is this? This lifting size is denoted by this number ZC, okay. So this is this table which is included here for the convenience, and now what is this minimum value of ZC which you should calculate, okay, right, which should be sufficient to basically encapsulate this k dash, right. What am I saying here? What is this KB? KB is basically the number of systematic columns in which this LDPC encoder arranges these input bits, right. This number remains fixed. The length of the column will change, but the number of columns remains same, okay, which is equal to 22, okay. So this product should be greater than k dash, okay. It can be equal to k dash also, okay, at least k dash, okay. If it is equal to k dash, then there is no filler bit. If it is greater than k dash, then filler bits are required, okay, because LDPC encoder can only encode k, not k dash, right. So if you, and as we have discussed earlier, you will have to write a small piece of code to basically see which one is sufficient, okay. It's basically searching. How do you implement the search? Again an IP, okay, wherein like how quickly you search through it, better your transmitter design, okay, or the LDPC encoder design. Now if you do this 22, ZC turns out to be 352, one of these numbers. It should be defined somewhere here. You can see that it has to come from here, okay. Let's see where is this, right. So 22 into 352 turns out to be 7744, and you take any other number, okay, it will be greater than 7744. You should not pick that ZC, because you have to pick minimum ZC, which basically ensures that k is greater than equal to k dash, okay. That turns out to be 352, right. You cannot have any other ZC lesser than this ZC also, because then k will be less than k dash, okay, which violates this condition. Now what is the conclusion of this? When segmented transport block size is not matched to suitable lifting size, which is happening here, okay, the segmented transport block is how much? K dash 7072, so not matching with the lifting size, okay, then filler bits are added, okay. And how many what is the number of filler bits? K minus k dash 672, okay, right. And we looked at another example also where the transport block size was small. That was the second example. We remember the filler bit number of filler bit was only 4, okay. So it depends on like what is the transport block size, okay, right. And this typically, okay, so it will be in this range, okay, you can keep reducing. And so what will be the output of this segmented module, okay, segmentation module? It will give you 4 code block of size k, okay, and which is k dash plus f, okay. Right, so 7744 filler bits with f is equal to 672. That's what, so you are ready to encode. And how many such modules you are going to, how many such code blocks you are going to get, it comes here, right. And now these numbers should be comfortable to all of us, okay, right. So B, this plus this is 28192, okay, and then it goes through this transfer block segmentation. What you get is 4 code blocks, first one, second, third and fourth, okay, right. And now this is 30976 because each one of the has a length 7744. But if you look at carefully, okay, what is the difference between the last code block and the first, all other code blocks, okay. What is the difference? The transfer block CRC sits in the last code block, okay, because that's what you are segmenting, correct, and naturally this will go to the last code block, okay, right. And then, so that's what it is. So this is code block CRC filler bit, code block CRC filler bit, here transfer block CRC, code block CRC and the filler bits, right, okay. And eventually, like, so this is basically the input, okay. This input is going to go to the LDPC encoder and now it is ready to encode because you have generated in such a way that it is like LDPC encoder can handle this, okay. So that's fine, okay. So what is happening again, okay. So what is this LDPC encoder input is k bits, right, that's what we just calculated, okay, right. LDPC encoder length, output length is basically a function of base graph. We have mostly been focusing on this, okay, but all the ideas remain same for base graph 2 also, and we understood why 2 different base graphs are there, okay. I have not included that discussion here, okay. So just to recapture, base graph 1 is optimized for higher code block length and higher rates, okay, right. Base graph 2 is optimized for lower code block length and lower rates, okay. So it was difficult to design a single encoder for both these extremes, and that's why Standard has designed 2 different base graphs, okay, right. So in our case, okay, so LDPC encoder output length is n, okay. See, this input is k, output is n, okay. Then I am writing this nr because we are looking at the rth code block, okay. So 66 into 352, okay, 23232. K is how much? We just calculated on the last slide, okay. And then what happens here is, okay, so filler bits, okay, are basically replaced with zeros because LDPC encoder is a binary encoder, okay. It can handle only either zeros or 1, okay. They are null bits, okay. So you need to insert them with zeros, okay, while encoded, and null bits are added back after encoding. That's crucial, okay, because they are dummy bits which needs to be removed before this data is transmitted, okay. So now what is the rate of each code block? Rate of each code block is 7744 by this k and n. It exactly comes out to be rate 1 by 3. Fine, okay. So mother code rate, right, okay. Why it is called mother? Because all other code rates are derived from this. Kids are derived from the mother, okay. That's the notion, okay. So then, but this is 1 by 3 and we know user never asks for 1 by 3. It will be some rate around 1 by 3, higher or lower, okay. So now, and this is what has been asked by the user in this case, 0.642, correct, okay. How do you derive it? That's where this rate matching comes into picture, okay. So rate matching, what it does, it matches this rate to the one LDPC encoder is generating and one which is asked by the user, okay. And how does it do that, okay. And for that you will have to see go through this, how many resources are assigned to this user. It's basically one PRB consisting of 14 symbols which has 168 subcarriers or resource elements, okay, right. 6 out of 168 subcarriers, 6 are reserved for pilots and so rest are used for transmitting data, 162, okay. So total number of bits which can be transmitted for 70 PRBs is basically 70 PRBs. Each PRB has 162 resource element, and each resource element can transmit now 4 bits because it is a 16 QAM. Okay, right? So you can transmit these many bits. Okay. Similarly, if it is 256 QAM, this number will increase. Correct? Okay, because you can transmit double the number of bits. Okay, right? Not double, sorry, 256, then it will be double. Okay, so total number of segmented code blocks is, we saw C is equal to 4. These are the total number of bits you can transmit. So for each segmented code block, okay, this is denoted as E, and what is this? This is G by C, right? This is 11340, right? For each code block, 11340 bits can be transmitted. Okay, so these are the numbers. Okay, but how many bits LDPC encoder is generating? N, correct? 23232. How many can you transmit? 11340. That's precisely what is rate matching. Okay, because you are generating at rate 1 by 3. You need to transmit at a higher rate. Okay, you are generating more parity bits than what the user has asked for. So what is the idea? That you basically drop these parity bits at the transmitter itself, so that you can match to the rate what user has asked for. Okay, right? So that's what is happening. And how is it implemented? It is implemented using this circular buffer. Okay, so you have generated N. How many are you supposed to be transmitting? E. Correct? Okay, right? E is 11340. That comes from here. G by C. Correct? 11340. Then there is the circular buffer. So first rate match block will be 11340. All of them will be same. This is for the second one, second rate match block. Okay, right? So you'll read 11340 for the second code block. Similarly for the third code block, and similarly for the fourth code block. Right? So rate matching implements this, is implemented using this circular buffer. Please remember, this circular buffer has not kicked in as of now. Okay, the working of circular buffer will kick in, let's say, if the hybrid ARQ triggers, if receiver is not able to decode data and you have to transmit some other redundancy version. Let's say you transmit RV3. Okay, RV3 will begin from somewhere here. We saw these numbers, we have calculated them also. Okay, right? So what will happen if you begin from this location? You'll wrap around and go back to the beginning and read those old bits. Okay, right? So that's where even you are dropping bits, circular buffer property will kick in when you start transmitting different redundancy versions. Typically RV3 you'll have to wrap around, right? And that's what it is. So now once you have done the rate matching, I'm not going to go take another example wherein like the rate asked by the user is lower than 1 by 3. Okay, right? So that is like, well, because of the scarcity of time, we'll not be able to do it here again. Okay, so now what happens after this is you have rate matched. Okay, then the next process is interleaving. So the interleaving, why is interleaving required? In order to handle the burst errors, which LDPC encoder finds it tough to handle. Okay, right? So, and what the key notion here is this row column interleaver. Okay, and how is it implemented? If it is QPSK, you divide the entire bit stream into 2 parts, stack them together. Okay, you are writing like this in a memory buffer. Okay, let's say with a two-dimensional buffer, just for our understanding, you write it like this, and then you read it like this. Right? Okay, and if you are reading it like this, this is the first bit from the second half. This is second bit from the first half. This is second bit from the second half. Right? And we saw how it is done, given in the standard, very simple instructions. Okay, right? So this is the interleaver output. Okay, I'm going to tell you how it is handled at the receiver. Okay, again, please don't search the standard for the receiver. Okay, so row size depends on the modulation order. Okay, this row size depends on the modulation order. Motivation is to avoid the burst errors. Okay, how burst errors are avoided, we have seen that. Okay, burst errors will happen here when so all these contiguous bits will be in error, but when you de-interleave them, the burst error will get spread over, right? So then let's go back. So what is following this interleaver module is the code block concatenation. Okay, one of the simplest modules. Okay, half day job for you to code. What is this? You put these code blocks together, and when will this happen? The number of code block is greater than 1. Okay, right? Otherwise, this will always be a pass through. Okay, for if c is equal to 1. Now, so the rate matcher output is for 4 code bit blocks is of length 11340. Total rate matched output is 45360. And this is what we were supposed to be transmitting. Correct? Okay, G. That's what it is. Okay, so G is this. Okay, we have come from 11340 from here only, right? This is E, this is G. Okay, so we put them together, we get back G. This is what you are allowed to transmit. Okay, now this is the last part which we did in last class also, but we are putting everything together. Okay, so interleaver avoids burst error. Scrambler helps you in maintaining the unit energy constraint. Okay, 2 different tasks. Okay, and we understood that in great detail. Okay, now this, what is the output length of this code block concatenation? G. Okay, right. So we consider a block of G rate matched bits and concatenated bits. So what are we doing here? We scramble them using this scrambling sequence. Okay, and that should also have a length G. Right. Okay. So what is this output? This output is a XORing of bitwise XORing of these 2 sequences. Okay, so you have 2 different bit streams. You XOR them bitwise, and that XOR sequence is B tilde of I. Okay, that's the scrambled output. Okay, right. So this is a pseudo random sequence. So we will see how this is generated also. This pseudo random sequence C. Okay, so that's the important part. Okay, now 5G allows these modulation schemes. Okay, 4, 16, 64, 256 QAM. Now what happens here is, okay, based on this, like what modulation scheme user has asked for, this will transmit 2 bits and this will transmit 8 bits. Okay, and then you take this modulation, there is a chain after this also. Okay, right, I am going to cover that in the subsequent classes. Okay, but this is, that chain is not standard specific. Okay, this is exactly defined in the standard. Okay, what comes after this is purely implementation. Okay, how do you design your system? Because what happens here is that this is, all this is done digitally. Okay, right, it is as if like you have a, like in a computer which is doing it for you, and that's what happens. In your mobile phone, these are these devices, digital signal process, or FPGAs, which do all this digital processing. Okay, but finally what you transmit is an analog signal. Okay, the waveform which is actually transmitted on air. Okay, right, standard doesn't specify how do you convert it into that analog waveform. That's where your real engineering kicks in. Okay, and I'm going to show you that, we will discuss that also, and that basically decides the complete network architecture also. Okay, right, so you'll see that the way these systems are implemented, this part is implemented in one part of the system. Okay, till okay, to a certain form, and then the rest of the processing which comes after this is implemented in another part of the system. Okay, so this is all basically digital. Okay, then what comes after this, I'll just like jump again and tell you. What comes after this is basically there are other modules, but typically there's a digital to analog converter. Okay, right, and then I'm taking liberty to like hide 1 or 2 modules that will come later. Okay, so there's a digital to analog converter which converts this digital bit stream into analog waveform. Okay, and that analog waveform basically needs to be up converted to the band which is allocated to a particular operator. Okay, that is called the RF up conversion. Okay, this plus some other modules plus this DAC is basically implemented on one platform. Other is basically called the RF front end, which is implemented on another platform. Okay, now so what happens at the receiver? You will down convert this RF signal. Okay, then you will what will follow after this RF down converter is ADC, analog to digital converter, because you have to do the reverse processing. Okay, right? And then there is a ADC sitting over here. Once it gives you that, okay, there's few additional modules. You've gotten back these samples. You can work with them. Correct? Okay. You do the complete chain, and then the data is basically, if everything works fine, TBCRC gets validated, then you have these bits which you can give it to the MAC. Right? Okay. So this is how a typical standard-based system is implemented. We'll look at all these details also, what comes here. Okay. So, but just to make sure that you don't get confused when it comes later, that sir only told earlier till the transmit chain is still here. I'm simplifying it for you so that we can understand the receiver chain which follows next, because it is for us to understand how, if you implement this, what goes in here. Okay, right? And that, as I said, we have to like do it on our own, use our fundamentals which we have learned earlier from other classes. Okay, so we'll see that. I'll stop here for now, and then we'll do this receiver processing in the next class. Okay, thank you.